Hello, I'm Mike Levin, and today I'm going to talk about one of the trickier but more fundamental concepts of information tech called virtual machines. Now, some people in technology immediately think of a company and product called VMware, or perhaps the free and open source project called QEMU. Now, these are in fact virtual machines, but they're not the kinds we're talking about here. These are full-fledged PC emulator / virtualizer, and I'm talking about something much more fundamental to computer science, which actually enabled the computer revolution. So you'll recall from a previous video, I talked about abstraction layers with hardware at the bottom, and then an operating system, and then your language, and your execution environment. And then finally on top, the apps. Now, I always mention the execution environment because there's a trick that's almost always used with programming languages today. There's exceptions, like the C languages that get compiled, but execution is almost always done on a virtual machine. In the case of Java, they call it the JRE, Java Runtime Engine, and .NET has one. Before that, there was one for Pascal, and so on back in history to the rise of popular computing, which is what I'm about to show you, because there is a chicken and egg problem here, which you might not really notice, but there is a chicken and egg problem right here. Because you can't make anything for the hardware unless you have the operating system, and if you don't have the operating system, you can't make anything for the hardware. So, and there's a tremendous variety of hardware, so this operating system has to be made for every single variety of hardware. So how was that handled back in the day? Well, there's this propensity in tech to make huge steps forward by simplifying previously over-ambitious projects. So there was an industry project called Multics, which a couple of rebels at AT&T named Ken Thompson and Dennis Ritchie simplified into Unix, which became the popular operating system to put it in at this point, especially back in those days and now again. Now, how that was done, how they got to Unix, is they used another over-ambitious project called the CPL, the Common Programming Language, which had by other people by that time been simplified to BCPL for the Basic Common Programming Language, and that became the B language. And B was the precursor to C. C was created as an offshoot of B in order to better create the operating system. Now, how did that work? Well, the problem, and I thought about how to draw this for quite some time, is that hardware has calls that can be made to it, instruction sets. It's like different shaped pegs, and when you make programs for it, you have to really be addressing that particular peg or instruction, or else your program won't make sense to the hardware. And this really goes on forever. What other shapes can I make? Well, here's a triangle. And well, you get the idea. This actually goes on for quite some time hardware can have quite a number of obscure calls, making it both complex and often cases sophisticated, special, or awesome. I'll just put special. All these extra instructions that you can call can let you do things faster and better than on competitive hardware. Now the problem comes in that no one knows those extra instructions that exist over here. So somewhere in the early 1970s, when the AT&T guys realized they needed a common operating system across hardware, what they did is they created a virtual machine that was keyed specifically for the hardware. Excuse my drawing, but you get the point. This piece was obviously made to fit right into that piece of hardware, snug as a bug. But it itself was not very fat. It only advertises other very common instructions. A smaller instruction set, a smaller set of keys, and this is the virtual machine. Now you would think the operating system was created on top of the virtual machine. Well, not so, because you still have the chicken and egg problem. They didn't have and also you wouldn't necessarily want the operating system going through a virtual machine and being slowed down. So the next thing that was written, but written only for the virtual machine, not the underlying hardware, mind you, and this is the trick of virtual machines that goes back to the rise of the internet. What this is the compiler. And this compiler is code that already exists and connects to all different kinds of hardware. Because only the virtual machine part, and I'm doing curly brackets here as kind of an inside joke, only the virtual machine has to be created for different target hardware. And then they could use the compiler to compile the operating system for the hardware. So the last piece to come in place that fixes the chicken and egg problem is the compiler compiles the operating system for the hardware. And this is usually, back in those days, it was almost always Unix, but these days it is also Linux. So yeah, that's the story of the virtual machine. These days the concept is almost everywhere, because it's so much easier to program things for a well-known intermediary layer. This is a layer, it's an abstraction layer, just like we had shown over here. And again, Java did it with the JRE, .NET does it, Pascal is one of the early languages that did it. And when you hear virtual machines used in the context of VMware and QEMU, they're just talking about third-party products that put one computer virtually inside of another. But it's important to know that almost all computer program code execution these days is actually going through some sort of virtual machine that exists right here, and that the concept of virtual machines themselves is nothing new. It goes back to approximately 1970, when a virtual machine was implemented with BCPL to create Unix. And the reason I use curly brackets here is that BCPL is the language that first innovated and popularized curly brackets, and that's the reason to this day why all the C heritage languages like C++, Objective-C, C#, all use curly brackets.